So,
Hey,
hello.
what's up?
Um, don't want to forget, on Wednesday, we're meeting at 4:30, right?
Yeah, and then I see you for 6.
Yeah, yeah. So, I wanted to let you know ahead of time. I have like an interview at 3:45 on Wednesday, so like I don't know how long it's gonna last. They're saying 45 minutes, but let's plan for like 4:40.
Okay, and do you want me to make this continuous with because there's because it's I see 4:30 to set 5:30 and then 6 to 7. Do you still want that half hour between?
So that was gonna be my next point. I'd like to actually have a little break in between.
Sure.
I'm gonna like eat. Because I usually like eat around that time, but since we had back-to-back sessions,
Yeah, yeah. So 4:45 to what, 5:45 and then
to like 5:40.
okay. And then 6 to 7, right?
Yeah.
Got it, got it, got it. What do you usually eat? I know
Oh, well, at this point, my regimen has,
everything is you're doing everything like completely
yeah, I have a crock pot and I make like
new.
six, no, not stew. Like, actually, I know that's what crock pots are usually used for, but I literally just make 6 to 7 pounds of chicken. Like, I just put 6, 7 pounds of chicken in the crock pot, high on 4 hours, and then I have enough chicken to last me like 7 or 8 meals. It gets super boring, to eat, but like I eat it with like rice. I like switch up the side, but it gets like crazy boring. But after my MCAT, I'm gonna like not eat chicken for probably like yeah, like a month. But it's just very efficient and like obviously like it's healthy. It's yeah.
Yep.
So that's what I do. I just like heat it up with like I have Trader Joe's right next to me. I get like the rice that you can heat up in the microwave and like avocado. It's like a good meal, you know?
Very nice.
Yeah. So I've been reviewing my full length. Been watching some of your old videos.
Oh yeah.
Um, yeah, yeah, with yeah. But I wanted to also go over some section bank stuff from before I even took my full length, just to like catch up, you know what I mean?
Mhm.
So we'll do this, and anytime we have left, we can spend on the full length three. But yeah,
Yeah.
yeah, okay. So it asks, you're able to see, it, right? Okay. Which type of enzyme catalyzes a reaction that directly activates or deactivates enzyme activity by covalent enzyme modification? Um, so from what I understand, that I don't remember the answer. I would think it's D because I remember that like pyruvate decarboxylase gets activated by being like dephosphorylated versus like phosphorylated.
Wait, what did say that again?
Pyruvate dehydrogenase, not decarboxylase. Dehydrogenase.
Yeah, that's uh um part of the what?
That's part of the what do you mean? Like it's kind of after glycolysis, right before Krebs.
What is that?
What
We,
is that stage?
yeah, yeah.
Uh,
We had this exchange before.
yeah, no.
I do something like this, it could help you jog your memory.
The Ceto Koi like shuttle. I forget. Like,
It has to do with that. So pyruvate can go into the mitochondrial matrix and go through the pyruvate dehydrogenase complex to turn into acetyl-CoA, and then the acetyl-CoA enters into the TCA.
yeah,
So 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 yeah, it's what takes that pyruvate and turns it into acetyl-CoA. And that's where the pyruvate dehydrogenase. um, enzyme is, along with two others,
Hmm.
right? So, okay.
Yeah, so that's why here I was thinking that the answer would be D.
Yeah, so, uh, okay, so tell me what these, I guess, choices do.
Well, adenyl cyclase converts AMP into cyclic AMP, or the opposite, I forget. But then that goes on to like activate pKa, and there's a bunch of like downstream processes.
Okay.
Um, and then ATP synthase, it com combines ADP plus like an PI, inorganic phosphate, and that creates ATP. It does that by like using hydrogens through the transporter, couples it, and then glycogen phosphorylase adds gly phosphate is added to glycogen, which makes glycogen 1 phosphate, glucose 1 phosphate, and then that gets basically converted to glucose 6 phosphate and then to glucose. And then protein kinase, I mean, it's a protein kinase. It's more general, but kinases can add or remove phosphates, and that's, yeah, it does that on proteins.
Yeah. With your STY, right? So they're asking, yeah, okay, activates or deactivates enzyme. Oh, wait a sec. Hold on. I think I read this wrong. Directly activates or deactivates enzyme activity of the same enzyme, I guess. I guess so. Okay. So yeah, it'll be kinase still because you can have ATP like so either you could have so you're gonna have STY take a phosphate from either ATP to give it to the enzyme for the enzyme to then give it to the substrate. You could also have something like pyruvate kinase in which you can take a phosphate from the substrate and ultimately give it to the so we could either do like ATP to ADP and giving the phosphate to a substrate, uh
Mhm.
or we can get a substrate with the phosphate and give it to ADP to turn it into ATP. Now, we usually talk about it this way, um but since this question's different from what I read it as first. It's saying that like what could make the enzyme itself activated or deactivated. So now I'm thinking about the kinase in between steps, like meaning before, so if the phosphate gets removed from the ATP and gets added to a substrate, in between the enzyme, the kinase itself is getting phosphorylated, right?
Okay.
Right? In both cases, like in between, like what it really means is like the enzyme can take let's say from ATP to ADP, the enzyme can gain a phosphate, and then it can give that phosphate to a substrate. So the only one that involves like activation or deactivation of the enzyme itself will then be the kinase because the kinase enzyme has STY amino acids that get phosphorylated regardless of if the kinase is going to ultimately phosphorylate the substrate or ADP. So, yeah. So these other ones like this could activate or deactivate, but it's downstream and they're asking for direct. And then same thing with B, it's just not direct. And C is going to be direct, however, like on the substrate, not on the enzyme itself.
So my example with the pyruvate dehydrogenase, that holds, right? Like that's a good example.
A dehydrogenase is going to be responsible for redox, and you're not transferring a functional group, so you're not having any covalent enzyme modifications there. Like what you're having is, a molecule a substrate that can be oxidized to reduce NAD plus into NADH when you have a dehydrogenase. So for the redox, but we're looking for something that can cause a covalent bond to, either show up or get destroyed in the enzyme on the enzyme itself.
Okay, then I'm still confused. Not gonna lie.
Yeah, so we want to ask ourselves which of these enzymes can participate, um, which of these, all right, so let me see. Which enzyme can, through a covalent enzyme modification, cause the activation or deactivation of an enzyme? Okay. Now,
Mhm.
so like adenylyl cyclase, that can take uh AMP and turn it into cyclic AMP, right?
Mhm. But those are substrates.
Exactly.
Hmm.
And ATP synthase can take, ADP and inorganic phosphate and make ATP, but it's still messing with the substrate,
Okay.
right? And then
Yeah.
glycogen phosphorylase is again messing with the substrate. Uh,
Hmm.
modifies glycogen by making glucose 1 phosphate.
Yeah.
The only one that would involve the enzyme being partaking in a covalent, uh, you know, reaction is the protein kinase because of exactly how I described it. The in between step is that the enzyme itself gets covalently modified because whether we are giving a phosphate, whether we're taking a phosphate from ATP to give to a substrate, or if we're taking a phosphate from a substrate to give to ADP, the what is the word? The middleman or whatever uh is the enzyme that gets phosphorylated in either case through STY.
So when like a protein kinase adds removes a phosphate, it phosphorylates itself.
Yep. So I could do something like this, ATP to ADP, and then the enzyme I'll put like in a box, and then enzyme is phosphorylated, and then um, substrate gets phosphorylated. So I drew here that when ATP turns into ADP, it gives a phosphate to the enzyme. So you go from the enzyme to the enzyme that's phosphorylated. And then the enzyme gives away its phosphate to the substrate, returning the enzyme to the unphosphorylated state and taking the substrate and making it into a phosphorylated substrate.
Mhm.
And then this can go backwards because if the phosphorylated substrate goes back and turns into the substrate, that means that phosphate is leaving, and it could be leaving to be added to ADP to make ATP. And when this happens, we can have the um, the enzyme go in like either direction. So yeah, does it kind of make sense what I do here? Like
Mhm.
ATP to ADP loses a phosphate, enzyme to enzyme that's phosphorylated gains the phosphate, but the enzyme can also will also give away the phosphate to like a substrate to phosphorylate the substrate, and the
Yeah.
substrate can actually give away its phosphate um, to ADP to recreate ATP, but this is going to also have, so I'm going to also do like the enzyme here, and then this turns into enzyme phosphate, oops, phosphate, and then when it goes back to turn into the enzyme, it can give the phosphate to ADP to turn into ATP. But the big picture here is this and that.
Yeah.
So this is actually a good question because it forces us to, because I haven't really thought about before like the in-between step. Like we're usually thinking about it like this, like ATP can get its phosphate taken away and given to a substrate, right?
Hmm.
Or we could have a substrate that has a phosphate, give it, give the phosphate to the, you know, ADP to turn it into ATP, right?
Yeah.
But in both cases, the in between step is that the enzyme gets phosphorylated, regardless of whether the ATP is getting dephosphorylated, which means the substrate will get phosphorylated, or then vice versa. But in both cases, the enzyme will be phosphorylated, and that's the covalent enzyme modification.
Got it. Okay.
Yeah. So if you want to take a screenshot of that, you could.
Yeah.
You did? Okay.
Yeah.
But yeah, that question, like the way that it's worded, is very important.
Mhm. So I got this right, but just want to go over it regardless.
Yep.
Um, so mechanical advantage is force out over force in, right?
Uh, and what is the difference between force out and force in?
Force out is if we don't use like the new whatever machine. Force in is if we actually like use the, whatever it is, like the pulley or the ramp,
Yep.
like it's the one after.
Now, what if you don't have the forces, but you have the distances?
It's distance in over distance out.
Good. And so the whole, and then what's the overall like idea behind mechanical advantage?
I mean, you're just trying to see what kind of advantage. Oh, actually, well, to be more specific, like you're putting less force over a longer distance.
All right, what's conserved, if anything?
The work.
Good. All right. And then I like that you highlighted constant speed. Good.
Yeah.
On an inclined plane, got it. That makes an angle theta with the horizontal. Um, the coefficient of kinetic friction is mu. What is the expression of the mechanical advantage? One second. Oh, we're moving back to chart. Sorry. Okay. Um, Mechanical advantage. All right. Okay. Maybe I can do this. And oh yeah, tell me what to do here.
Yeah, so I want to ask if I could actually try it. Well,
Go for it.
yeah, so we got the block, and then we're gonna have the downward force FG make this triangle. I always forget how to draw the triangle, honestly. I end up like remembering at one point. Okay, here I remembered it finally. Um, this is theta, which is like the same as this theta.
Yeah.
Um, okay, so yeah, whatever, you get the point. And so yeah, you got there's the sine and the cosine components. When you have this like downward mg. Now the sine one is like here. So if this is going down, this is like mg sine theta,
Okay.
right? And then like the one that's um yeah, like the vertical one is mg cosine theta.
Uh, okay, go on.
But the thing here is because it's a constant speed, we need to also remember that force of friction is mu mg cosine theta. And so this um so like we can equal from what I remember, we can like equal mg um wait, so hold on. Force of friction equals mu normal force.
Yeah.
Normal force here, okay. Normal force here is co mg cosine theta. That's the normal force, mg cosine theta.
Mhm.
And then that is the frictional force.
Yeah.
And we can equal u mg cosine theta to mg sine theta,
Mm-hmm.
factor out the mg.
Yep.
The main thing that I just wanted to confirm, so okay, I remember how to do this, but the main thing is like setting it, okay, so we set it equal, but okay, and like let's say, so we do this and we get, I mean, you can take over if you want. I'm just bad at the drawing on this, but
Mm-hmm. So, all right, so you drew it, and we wanna, so if we draw our free body diagram, what do we do after that?
I'm not like, what do you mean?
So whenever we draw our free body diagrams, what we do after is we use Newton's second law.
Okay.
And I think you're kind of doing that here. So we know that um, that Newton's second law is the sum of all the forces or the net force, and we would have a force of gravity in one direction and a force of friction in the other direction, and then that'll equal ma, right?
Hmm.
And what can we do from here?
I mean, we could substitute um f of g is
Well,
anything
before that,
what?
before that, so
Like
what you do?
solve for I don't know what we can solve for though, but like A, I guess.
What would
Why though?
a be?
I mean we would just divide both sides by m.
Oh no, I mean here,
0.
0, right?
Okay.
And that, so like what like you're not doing anything wrong here. Um, but it's always best to keep things as variables as long as you can,
Yeah.
because so we can set it up properly. So instead of just starting to plug in mg stuff, uh I want to set it equal to like to ma, right?
Hmm.
And if it's a constant speed, the acceleration is 0. So now I have, F g minus F friction is equal to 0. And now I can do what you did here, which is I can add the F friction on both sides, right?
Hmm.
And it's just a lot more cleaner to do it like this. And then we can put in, the values. So like mg sine of theta is equal to mu times mg cosine of theta,
Right.
right? And now we can divide mg on both sides to get
Hmm.
sine of uh sine sorry si yeah sine of theta is equal to mu times cosine of theta, and now we have to turn it into the mechanical advantage. So what would that entail?
So, okay. Well, we're looking at force out over force in. So force in is what we would have with our incline plane.
Good.
And that would be that's the thing. I was a little confused about that part. I mean, you're saying it's Fg minus F of F, but they're
So
equal.
all of this is if you're using the machine.
Yeah.
So, and mechanical advantage is comparing if you're using a machine to if you are not using the machine, right?
Hmm. Okay.
So if you're not using the inclined plane, right, the force of it would be what?
Like that's the thing. I don't really know. 0, 1.
So this box is on a plane here, and now in this, it's not.
I mean, if it's just constant speed is 0.
No, no. So what I'm saying is, sure, on the inclined plane, constant speed is 0, and we got all that stuff down, right? But mechanical advantage requires us to compare with the plane to without the plane. So we know for the inclined plane that it's going to be this like mg sine thing, right? But what about if we're not using the inclined plane?
Mg.
just mg, right? So it should be mg over the um oh well, okay, I guess this doesn't help us too much like that, but we can think of it as like back to this. So I'm gonna actually for the force, because you're like, okay, this difference in the forces is gonna give you the force, the net force of using the inclined plane, right?
Okay.
Meaning um the mg sine of theta minus mu mg cosine of theta. This is the net force if you're using the inclined plane. So this is our F, our force of the incline.
Mm-hmm.
So now we can plug that in here. We could also factor out the mg to get sine of theta minus mu cosine of theta, right? As our F input.
Mm-hmm.
Now I can plug it in here. So mg parentheses sine theta minus mu cosine of theta. The mg's cancel. And so our answer is just 1 over sine of theta minus mu
There's no
cosine.
minus
Uh,
in any of the answers.
oh,
Yeah.
well, okay. Well, let's see. So we definitely are not multiplying them. We're definitely not. I mean, we need to have like the sine theta term attached to nothing and the mu attached to the cosine term. So this has the mu attached to the sine term. No. This has sine times cosine. No. Um, so this would definitely be the best one. But let's see what I did here in terms of why that's a plus and not a um F equals this. They're in opposing directions. Sine theta plus this direction. Force of mechanical advantage ratio of the object weight mg and the applied force to move the object up the incline. Oh, moved up.
Oh wow. Okay. Didn't realize.
Okay. That's why we are adding them. If it was just stationary, so I guess I was taking it to mean that it's still coming down,
Yeah.
but at constant speed, which is when you would have this, the subtraction of the forces. But if they're saying it's still being moved up, we need to go, push it up uh by that amount that otherwise would be taken away. Like if we're pushing it up, then the force of friction and force of gravity, like, we would add them together because we're moving it up.
So if
But
we're moving something up an incline, we add f of f and f of g.
yeah, so for instance, if the like so what I put in for this is it just falling down at a constant speed. But if you want it to go up at that constant speed, instead of, subtracting them, you would add them because that's what you would have to overcome.
So basically that.
Okay. When you're pushing something up an incline at constant speed to find the total force, you add the force of gravity and the force of friction. Um, let's see. Okay, I'm gonna write something. Oh, you said another thing. I know, Jacob. Or if a mass slides down inclined plane at constant speed, the force of friction is equal and opposite to the force of gravity. However, if you want the mass to be pushed up the inclined plane, you must overcome both the force of gravity and that's bringing it down and the force of friction, which is going to be, opposing the direction that you are pushing it. Because the force of friction will always go in the opposite direction of movement. So that's why, if the mass is moving down the inclined plane, the gravity is what's bringing it down, and the friction is what resists it going down. So the force of friction is in the opposite direction, up, right? But if you want the entire mass, and that's, if it's falling down, but if you want the mass to be pushed up the inclined plane, you need to overcome the force of gravity, the mg sine theta. But if you're pushing it up now, the force of friction is going to be in the downward direction because it opposes that of the motion. And that's why you want it to move up. You need to overcome both the gravitational force that brings it down in both cases, and the frictional force, which brings it down only in this case if you move it up.
Oh,
Mhm. Okay, let's see. 1 mole of ideal gas undergoes a thermodynamic process in which pressure doubles and volume halves. What is the value of the molar heat capacity of the gas during the process? Oh, can you hit the annotate?
yep.
molar heat capacity. Now, heat capacity we know is how much heat in energy or joules something can absorb before it goes up, a degree in temperature.
Mhm.
So, like, it wouldn't be the ideal gas constant because that would be in some type of energy per moles times like degrees Kelvin or something. Um, so it shouldn't be that. And then would it be undetermined? Would it be zero? Would it be infinite? Oh, heat capacity. Maybe this is well, I guess I could talk about the temperature difference. Like, okay, if the molar heat capacity was zero, it means that it can't absorb any heat. Um, and that would mean that, yeah, this is tough. So, okay, I know it's not going to be that. I don't think it's going to be that. Undetermined versus infinite. Infinite means it can absorb an infinite amount. Well, let me see. Molar heat capacity is heat capacity divided by moles. Oh, okay. Wait, yeah, okay. Divided by moles. Amount of heat required to raise 1 mole of a substance by 1 degree. Um, so okay, I think so when we use Q equals MCAT, we're using the specific heat, um, which is like how much heat energy like a gram of something can absorb before it goes up by 1 degree like Celsius or Kelvin. Um, but the molar heat capacity, I think, is going to be closer to like the phase change between like, I guess. Hmm, okay. Yeah, I think it would be okay, so if we are indeed talking about the phase changes where the temperature does not change, and if heat capacity is the amount of heat energy you can absorb that causes a 1 degree change in temperature. If there is no change in temperature, then the heat capacity should be infinite because an infinite amount still won't change the temperature. So I think
Mhm.
that's going to be uh the answer. Okay. the molar heat capacity equals the heat exchanged in the process divided by the temperature difference between the final and initial thermodynamic states. According to the ideal gas law, the final temperature is the initial temperature because the product between pressure and volume is the same in the two states. As the heat is not zero and the temperature difference is zero, yeah, the molar heat capacity is infinite. So the way to do this was first write PV equals nRT, and you can see that, sure, if pressure doubles and volume halves, we're not changing anything, right? We still have it equal to nRT. And if it's
Mm-hmm.
equal to nRT and we don't have a change in temperature, right, we could determine that it's undergoing a phase change, or at the very least, it's undergoing no temperature change. So if the heat capacity is how much heat something can absorb before it goes up in temperature, and the temperature is not changing, that means that the heat capacity would have to be infinite because no amount of heat capacity, no, sorry, yeah, no amount of heat can change the temperature.
In one ear, out the other, basically for me.
Hmm. So
Um,
let's say that pressure doubles and volume does not have, right? PV equals nRT. Like
mhm.
really would be considering two like scenarios here, meaning like regular when it's PV equals nRT, and then when pressure doubles. If pressure doubles, we should see a change in temperature on the right,
Yeah.
right? So when we compare PV equals nRT when it's just regular to when we double uh pressure, that's going to give you a different temperature.
Mhm.
But and then same thing with if you just have the volume, you're going to get a different temperature. But if you both double the pressure and have the volume, this term does not change, which means that this term won't change, which means
Okay.
temperature won't change.
Okay.
If temperature does not change, and if heat capacity is defined as the amount of heat energy something can absorb before it goes up 1 degree in temperature, like if the molar heat capacity was like 4 joules, it means that it can, if it absorbs 4 joules of heat energy, it'll go up like 1 degree in temperature.
If something has a peak capacity of that,
Yep.
it'll go up. If it has a heat capacity of 4, like,
Uh-huh.
joules per kilogram times K.
Yeah, it'll be like yeah, it'll be like over like it it won't have the kilograms part. That's going to be for specific heat, but yeah, same idea.
And what's the difference between specific heat and,
Just the mass term.
but then like how does the heat capacity even work if we're not basing it off moles or kilogram or like or kilograms or moles like
Well, we are this one that we're talking about, we are basing on moles,
Mhm.
right?
But how does heat
Hmm.
capacity work?
So, okay, yeah. So specific heat capacity is going to be involved in, this formula, and mass is in grams, temperature is in Kelvin. It could also be Celsius. So your specific heat would have to be like some energy term over some, mass term times some kilogram term, like that, right?
Yeah.
But for like just so specific heat could be thought of as heat capacity applied to a mass, whereas molar heat capacity is like specific heat, but instead of applying to a mass, we apply it to a mole.
Mhm.
Okay. Now, what that means is that, but yeah, ultimately, what you're gonna get for like, so this formula, you're gonna get that as well. Like, we could just say that it's gonna be Q equals, instead of mass, right? It'll be N, which stands for moles, like here.
Mhm.
And then instead of lowercase c, which is specific heat, which is for masses, we should have, I mean, I guess it can show up as a uppercase C. Um, but what that means is just it's the molar heat capacity,
Sure.
right? So uh now you're also going to have, a delta T term here, which means that so it just means that the molar heat capacity is the heat energy it takes to raise 1 mole of something 1 degree, Celsius or Kelvin.
Mhm.
Okay. So now, if they're telling us that the so first of all, if we just doubled the pressure, right, we would have likely a double in temperature, or at least some change in temperature. And we
Yeah.
can compare it to when the pressure is not doubled.
Mhm.
See that there is a change in temperature, and in that case, we can get like a value for the molar heat capacity.
Mhm.
But since there is no change in temperature, that means that our this uh molar heat capacity, which again is the amount of heat it takes to raise 1 mole of the substance 1 degree, like Celsius or Kelvin, since we are not raising the temperature at all, that would mean that our molar heat capacity would have to be infinite, because it means that no amount of heat energy will change the temperature.
Okay. That helps a bit. It's
Hmm.
good. It's good. Good. Good.
Yep.
Okay. Yeah, it's like really like you need to really intuitively understand
Hmm.
the capacity of this problem. Like this, yeah.
Yeah. Yeah.
Um, okay. And this is the last one for today.
Um, Half submerged, okay. That, is always a little bit more annoying, but it's fine. Okay, hollow cube floats half submerged in oil. All right, now, and it's not in water either, so that could be annoying, especially if they ask for specific gravity, which doesn't seem like it. But okay, oil of density 800 kilograms over cubic meters. The cube edges are marked every 1 centimeter. What does that mean? Cube edges are marked every 1 centimeter. Okay. Minimum. I guess it means like either this is the cube and one side of it is
Yeah.
1 centimeter, or
I know. Yeah, I know. I'm pretty sure it's like the first one, the former, but yeah.
what is the minimum density of a liquid that can be determined by reading the mark at which the cube floats? Okay. Hmm. Minimum density of the of the liquid. Um, Minimum density. Okay, let's see. Hmm. Okay, I mean so all of these choices are smaller densities than the oil. So if it's a oil density of 800, it's halfway submerged. If the oil density or the liquid density, whatever, is smaller, the density of the fluid is smaller. Okay, the denser it is, it's denser, it would be harder to sink in it, and it won't be as submerged, I guess. Let's see. Okay, wait, they do mean marks like this, I think.
Really? Wow.
Because it's saying how what's the minimum density of a liquid that could be determined by reading the mark at which the cube floats. So like the markings like this.
Mm-hmm.
So we can see like, okay, at this oil, in this oil, it's the marking that is halfway, I guess. Um, and then by reading the marks, you can see if it's going to be like less submerged or more submerged. So if it was a, so if the object's density is, let's see, the object is less dense than the fluid, it should float higher. If the object is more dense than the fluid, it should float lower. Since all of these choices are lower, well, actually, I don't know what the, okay, well, hold on. Okay, so I get it, I think. So gravitational force and buoyant force produce it, and so the volume of the fluid displaced is 1/2 of the volume of the object. And let's see, minimum density. Okay. So if the density is 800, that means half of it is submerged, and they're asking minimum density that can be determined by reading it when it floats. Um, so like if it was the fluid was twice as dense. Okay, hold on. If the fluid was twice as dense, this would be completely floating, I guess. So if the fluid was halfway dense, if the density of 800 makes half of it submerged, if you make the density half of the liquid, I believe you should have rho object volume object G rho fluid 1/2 volume object G. These are equal. These can cancel. These can cancel. Got it. You need your fluid's density to be 1/2 of that of the object, and if it's halfway submerged when it's a density of 800, and we want to figure out the max density at which we can read the mark, which I guess means that can be determined by reading a mark. So I guess that means that like if it's the last mark that you can still see, so it's right before it's completely submerged. So I'm gonna guess that it'll be half because of this.
How did you derive like this?
Oh yeah, that's just from your free body diagram of like this is the force of gravity, this is the buoyant force, and so the force of gravity is mg, which is also rho of the object, volume of the object times g, and then this is rho of the fluid, volume of the fluid displaced, which is 1/2 volume of the object times g. So if these are, like equal, we can just do like rho this, oops, volume object here, g minus rho fluid 1/2 volume of object times g. We can cancel this and this.
Like they're equal to each other, right?
Uh-huh. So
Yeah.
it could be like um uh, that wait is equal to 1/2 of this. You can do that. So the density of the object is 1/2 the density of the fluid, and like I think that'll give us C. Um, yeah, I was confused about what they mean by reading the mark and the marks, but I think that um, and then I guess also since we know that rho of the object 1/2, yep. So okay, the cube sinks in a fluid having a density less than the cube density. And yeah, they do mean the thing with the marks. So if it's completely submerged, if there's marks every centimeter on the block, like this, right? And then we submerge it. Oh, well, whatever. It's messing with my drawings. But the idea, okay, yeah. So like here. So like the cube with all the markings. And so if it's like very, very much submerged, we should see like one of the markings. But if we don't see any markings, it's going to be completely submerged. I think so. That's what they mean. So the minimum density of a liquid that could be determined by reading the mark at which it floats, that's going to be like what's the smallest density for the fluid for the cube to be like practically like mostly all sinking or sunk or submerged. Oh, and they even did like they solved for the cube density, which I guess you can do as well. Yeah. But well, that's what I did, but I did it with yeah, that's what I wrote, right? The rho 1/2 volume of the object is equal to volume of the fluid displaced. So yeah.
You see what I'm drawing?
Yep.
So my only question is, this holds true, right? Like, imagine instead of water, it's oil, right? Like this specific heat, specific gravity, but for oil. Like, if something is submerged in oil, like if it's 50%, it would like this setup works, right?
Um, well, you're doing like this is the density of the oil, so maybe what you mean to do is
Oh,
relate the volumes. So like volume of like all right, so volume of the oil is 1/2 the volume of the object. So volume, 1/2 volume of the object, volume of the object is equal to the rho of the, so this is the volume of the fluid, right? So this would be the rho of the fluid over the rho of the object.
Hmm.
And then like, yeah, this can cancel. So this means that, yeah, it means that 1/2 rho of the object is equal to rho of the fluid.
Okay. All right. That's it for today.
Mm-hmm. Let's see. Should be 88 for today.
All right.
All right. Awesome. I will see you tomorrow at 6 Eastern.
Yes.
Take care.
Bye.